Polycondensation polymers in Chapter A. And this was the last slide that we have discussed on the polycarbonate polymers. A carbonate contains ester group and ether group connecting together. So you have a CO3 groups as a functional group. Okay? And this polycarbonate has been used as a small aircraft penetrating from North Korea to South Korea. Perhaps you have heard about the polycarbonate. Okay, the outer shell is made of polycarbonate, and it doesn't. We cannot detect the radar through this the plastic, and perhaps we can discuss about what happened with the radar detection of this polycarbonate later on. But important aspect is that you have heard about the loss modulus in dynamic mechanical analysis. So when the plastic has a big loss modulus, then you will not be able to get the detection from the radar because of the dissipation of this vibration. So this polymer usually is lightweight, and it doesn't cannot be detected by the radar, so it could be used as a coating material for your stealth, the aircraft as well. But anyway, this is the very important aspect of the polycarbonate, and was invented by General Electric. And this, I know that we have emphasized that this has a very good transparency, so it could be used as a glass in your the glasses, so you will be able to make the helmet and other detection purpose. The next polymer that we can discuss is about the polyurethane. Okay? Polyurethane contains amide and ether. Okay? So I think we have discussed about the chemistry, where you have an isocyanate group containing monomer, and the diol will react with addition reaction, but step cross polymerization. So you form the polyurethane between this reaction. The alcohol, diol, with the isocyanate. I have elaborated the three different types of the isocyanates. We have aliphatic isocyanate, aromatic isocyanates. So the isocyanate was attacked by the alcohol, so you form the urethane. So reacting between the diol and HMDI, diol and diphene and methane diisocyanate, and TDI, MDI and TDI will result in different type of the polyurethanes. Now, when you think about the property of the different polyurethane, the first polyurethane could be quite flexible because of the aliphatic chains between the urethane linkages. Whereas if you have aromatic groups, then you're expecting to have pretty hard and rigid polyurethanes. So depending upon the monomer that you're using, you will be able to make the flexible polyurethane or very hard polyurethanes. So when you think about the artificial leather, artificial leather, 인공 피혁, 인공 가죽, artificial leather, it's flexible. So you can think about the perhaps it could be made from HMDI rather than aromatic containing isocyanates. Whereas if you think about the polyurethane in your shoe sole, okay, 뒤꿈치, 뒷발이고요. Shoe sole is not flexible; it's pretty hard. So those shoe soles could be made from one of these, okay? Because you need to have a very rigid property or the resilience. So depending upon the type of the isocyanates that you're using, you can make a different type of the polyurethanes, or you can mix some of these. Okay? So that's the polyurethane chemistry, but be careful that the isocyanates are very water sensitive. So if there is any water vapor or small amount of water present in your reaction system, that will terminate these isocyanates. So the chemistry will not be exactly the same as what you have intended. So water vapor or water should be removed before the reaction. Of course, if you have the water vapor inside of your container of this isocyanate, you lose your HMDI or the isocyanate contents. And finally, you can make a polymer through this interfacial polymerization reaction. Okay, I heard that you have already gone through with the interfacial polymerization reaction at the laboratory, the experimental class. But for those of you who have not, attended this course, we have prepared the some of the monomers for your demonstration. Okay? Now, interfacial polymerization is the concept where you form the polymer between the interface. Okay? In other words, we have acid chloride in the organic solvent. So the organic solvent is heavier than the water. So the organic solvent phase is residing on the bottom of this the flask. Whereas if you put the diamine in water, and if you mix it up, because of the difference in the density of the organic solvent and water phase, aqueous phase is the upper part. Okay? Now, the acid chloride and diamine only react at the interface because you have many of these acid chlorides here on the bottom, whereas diamine is isolated, particularly residing on the upper part. So the only ways of meeting these diamine and acid chlorides are on the interface. So if you put those two monomers in different organic solvents and water, you can see immediately the formation of the polymer. But if you remove the polymer, then you form the new interface without the polymer phase, so that you form continuously the polymers. If you remove the polymer, then you can continuously produce the polymer at room temperature. And this is what we call interfacial polymerization reaction, or in the scientific term, this is called Schotten-Baumann reaction. Okay? You can form the polymer in two ways. Okay? You can form the polyester, or you can form the polyamide. Okay? Polyester can be produced from the acid chloride, diacid chloride with the diol reaction. So you remove the HCl as a byproduct. Now, the acid chloride with the diamine will produce the diamines, the amide. Okay? But HCl as a byproduct, you do not need to remove this because it's a very quick reaction, and the HCl is present in one of this, particularly in the aqueous phase. So if you put the sodium chloride here, you can, neutralize the HCl. In other words, you can remove this HCl without any vacuum or anything. So this is a very simple and easy the polymerization reaction that you can experience. You can form the nylon 6/6, okay, with the adipole chloride and hexane and the diamine in the water. So I just wanted to show you the chemistry here. We have a hexamethylene diamine. We have a sevachroyl chloride. So you can form nylon 610 with this very simple chemistry, which is very similar to this slide. So I wanted to show you. So this is diamine, okay? Diamine in the in water, okay? In the hexamethylene diamines, and this is the acid chloride, okay, with the sebacoyl chloride. So I just wanted to put. Let me just wear this glove. You can see a little bit of frame, a little bit of vapor because of the very rapid reaction and generation of HCl. And okay, so I have a diamine. Diamine in water is lighter than the organic acid, organic solvent. So if I will just put it over here, you can see the isolation of these two layers, okay? But if I will remove, you see the solid part continuously coming out as a polymer, right? As a polymer. So this is very easily, you can form the nylon 610. So you can form the nylon 610 very easily, and it's the same as this slide. So what happens is that, you know, at the interface, you form the polymer, which is in white color. So there is no further reaction because polymer will block the contact between the diamine and the acid chloride, okay? But if you remove this polymer layer as a barrier, then the diamine and the acid chloride will meet again, so that you form continuous the polymer, so that I can remove, you know, polymer as a film, or as a fiber, okay? So if you think about this, the chemistry, then you will be able to make the polymer in two different baths. So I used one single bath, but if you have two baths, okay, one containing acid chloride, the other one containing diamine, what you can do is that you have a roller of some support and soak the first monomer, okay, and nip them. In other words, if you roll it, the excessive amount of the first monomer, okay. So the first monomer is coated on top of the support, and if you put it in, and this coated support with the monomer one will be immersed in the second bath containing the second monomer, you will see immediately the polymer formed on top of your support. So this way, you can roll it up and make the interfacial polymerized, the sort of a membrane. It could be used to desalinate the water, particularly the seawater, and also in this way you can make the reverse osmosis membrane to purify your water. Okay, water purifier. Okay, in your household, in your home, is made out of this chemistry. Okay, the Ungjin Chemical is producing in Korea, using this chemistry, the big machine. Okay. So this is the typical example of the interfacial polymerization. So you can make a nylons or nylon 610. Depending upon the monomer, you can make a different type of the polymers. Just to show you the aliphatic amines here, because aliphatic amines are easy to react, whereas if you have aromatic diamines and aromatic acid chlorides, you will need a special treatment. Okay, so aliphatic ones are easy to demonstrate in your case. So with that, I think I can show you the chemistry of the condensation polymerization or step course polymerization, and I try to demonstrate to you the examples of the polymers. So if you have any questions, please let me know in chapter A, about chapter A. Okay, so we expect to have your answer sheet of your homework number 1 by next Wednesday. So that's about the step course polymerization, and let's talk about the chain course polymerization in chapter 9. In this chapter, we will emphasize much on the kinetics of polymerization reaction between the step course and chain course polymerization reactions. We have talked about the kinetics of the step course so that you will be able to solve these problem sets as a homework. But in chapter 9, we need to describe again about the kinetics of these chain course polymerization reactions. Remember that we have three very important steps in chain course polymerization reactions, right? First, initiation, propagation, and termination reactions. Initiation, propagation, and termination reaction. 3 very important steps. Okay. But if you have additional termination reactions coming from the other reaction medium, we call that as a chain transfer reaction. Okay? So so we will discuss further about the chain course polymerization reaction in this chapter as well. Okay, I think you have learned about the 3 important steps in organic chemistry. Well, we need to be more in details about the chain course the chain transfer reactions as well. So I will describe to you later what's the chain transfer reaction. Okay? What are the very important aspects? Well, because of the kinetics, we have a chain length, of course. Chain length. Okay, chain length means that how long your chains are. But what about the kinetic chain length? What about the physical chain length? So we will describe what's the definition of a kinetic chain length and physical chain length. Okay? In short, kinetic chain contains active sites, radicals. If you don't have any radicals in your chains, it's called physical chain. So we have a kinetic chain and the physical chains during the polymerization reactions. Kinetic chain length means that you have a chain length divided by the active sites. Okay? If you have one active site, one radical in your chain end, we call that as a kinetic chain length. Okay? But if you don't have any radicals, we call that as a physical chain, and the physical chain length can be determined by degree of polymerization, repeating units, stuff like that. Okay? So in this case, we will talk about the structural units and repeating units again in this case. Okay. Okay, we'll talk about disturbance effect, but I think we can step. Okay. In the chain course polymerization reactions, we have different types of the reaction reactions. If you have a vinyl group is regarded as a bifunctional, right? So the double bond with the electrons residing in two carbons will be cleaved, will be broken into two pieces. If it's homogeneously cleaved with the same distribution of electrons in two carbons, we call it as a radicals. Okay, so you generate the two radicals out of the double bond, one double bond. If the electrons is not, if this double bond is not cleaved homogeneously or heterogeneously, in other words, if the electrons will be moved to one carbon so that the electron density of the one carbon is richer than the second carbon, we have a negatively charged carbon and positively charged carbons. Okay, depending upon how the negatively charged, what is the type of your chain end, whether this chain end is a cation, we call it as cationic polymerization. If the chain end is negatively charged one, we call it as anionic polymerization reactions. Okay, so we have a radical polymerization and an ionic polymerization, where we have a cationic and anionic polymerization reactions. We have a group transfer polymerization or coordination polymerization, depending upon the catalyst that you are using. So we'll discuss about this new type of the polymerization reactions later on. First of all, if you think about the chain growth polymerization reactions, we need to think about the difference between the chain growth and the step growth polymerization reactions again. Okay, okay. If you remember this, the graph, where this is the conversion versus the molecular weight. What is the step-growth polymerization? A, B, C. A should be step-growth polymerization reactions. What about the chain-growth polymerization reactions? C, right, is following this curve. What about B? We call it as a living polymerization reactions. But we have not talked about the living polymerization here, but we'll show you what are the living polymerization. And in short, this is the anionic polymerization reactions. Anyway, step growth and chain growth polymerizations are different in this graph, so that we can describe the chain growth polymerization reactions. Monomer concentration decreases steadily throughout the reaction, but the growth of the reaction adds at one at a time to a chain, so your molecular weight will increase initially. Whereas the high molecular weight polymers are formed at the beginning, and the long reaction time does give high yields, but does not affect much on the molecular weight of your final polymers. Whereas the reaction mixture contains only the monomer and high polymer, and the growing chain's concentration will be very high. Whereas the step-growth polymerization, molecular weight increases steadily, slowly, and high molecular weight polymers are found at the end of your reaction, finally. And long reaction time is required to get the high molecular weight polymer and high yield. So you need to wait for a long period of time for your high molecular polymer formations. So there are two different, many differences between chain growth polymerization and step growth polymerization reactions. And you need to remember this, because if you're, I think you will be asked a lot of times, if you were asked to, whether you have taken the polymer chemistry course, then you were asked from your interviewee that what's the difference between step growth and chain growth polymerization reactions, and you will be able to answer correctly. Okay. So let's talk about the chain growth polymerization reactions. First of all, the initiation. Initiation means that you need to have an initiator. We will discuss later what are the important initiators in this case, but you need to have an initiator. Initiator could be generally the hydroperoxide or azure isobutyronitrile. So you have symmetrical compounds that will be broken into two pieces, which generates the radicals, and the initiator will usually broken into two radicals. In this case, now it will be if this is the general chain growth polymerization reactions, this dot is not actually the radical itself, but it could be radical or could be ions. But let's say that we have a radical polymerization reactions first. So radical initiator is broken into two radicals, and you have a decomposition rate constant, which is called the KD. In this case, you have two radicals. Now, AIBN, azure isobutyronitrile, containing, you have four carbons, so it's called the butane, or isobutane, or and this is not methyl group, so and nitrile, so we call this as isobutyronitrile. Isobutyronitrile. This N double bond N is called azo group, azo, AZO, and the azo. So you have two the isobutyronitrile, so we call this as azo isobutyronitrile. Now, bond energy of this azo group is quite low compared to the carbon-carbon the bond energy, which is about 90 to about 100 kilocalorie per moles. So when you have the energy exposed to this initiator, such as heat at around 60 degrees C or UV light, then the easiest way to be broken is this bond, because this is the weakest point. And it's broken into two radicals with the isobutyronitrile radical, and nitrogen is generated. Nitrogen is meeting together to come up as a inert gas. So you have two radicals here in this case. Now we describe this as R dot. R dot means radical. Radical can meet the monomer. Monomer in this case could be a styrene monomer. Styrene has a one double bond, so it will be cleaved into two. So one radical from the initiator will attack this double bond, and your one radical from this double bond will meet the radical from your initiator and form the covalent bonds. And at the end of the chain, particularly the alpha carbon, you have a radical. And this is quite unstable, but anyway, it will be, this is the initiation step. Now, in the second step, we have an initiation reaction rate constant called Ki. So if you think about the radiation Ri, is equal to Ki times the concentration of reactants R dot and M. So we can describe this reaction. Ri, initiation rate, is the Ki times monomer concentration in initiator radical concentrations. Now, because we have a monomer concentration here in this case is a constant, because you know this, the initiator concentration, because you put your monomer by yourself. So it's a known constant. Ki is a constant. The only thing that we do not know is I dot. Okay? Well, we know I, but we do not know how many radicals we have. Anyway, we can describe this. We can describe this I dot in terms of Kd and I later on. So we will replace this I dot in a known constant and variables. Remember that Kd here is about 10 to the minus 4 to 10 to the minus 6 liter per mole sec. Okay? So we'll come back. What's the meaning of this Kd? Okay, this is the the preliminary step of a initiation reaction. In the second step, the propagation, the Rm dot, which was formed here, Rm dot, which is quite unstable, the initiator and the monomer radical. At the end of the chain, you have radicals. Rm dot will attack the second monomer. Okay, so you have Rmm dot, which will react with the M, another M. So you have a M3, M4, stuff like that. So you have a continuation of a repetition of the same step as a propagation. Now, each step, we have a Kp, which is a propagation rate constant. Propagation rate constant is the same because we have assumed that you have a equal functional group concept. Freud says that it doesn't matter whether you have any the size and reactivity is not affected by the size and complexity of your reactants in the polymerization reactions. So Kp is the same. So each step is Kp, but you have many Kp reactions. Now we can describe this propagation reaction with the Kp and concentration of this Rm dot. So as a rule, because we have a monomer, concentration in the reactants, we have a M dot. M dot is the concentration of your radical at the end of your chain. Okay, as a reactant in the left-hand side, you have a M and M dot times Kp is equal to propagation rate of your the overall reactions. Okay. Kp in this case is about 10 to 2 to 10 to 4 liter per mole sec, which is much higher than Kd. Okay. So once you have a decomposition of an initiator, your propagation reaction rate is quite faster than the initiation rate constant, so that you can expect that you have a very good, very rapid, very fast, reaction of the radical polymerization reactions. Okay, so that's the propagation reaction. In the termination reactions, we have two different modes. Okay? We have radicals, two radicals. Okay, in other words, you have a growing chain with the high molecular weight or middle molecular weight, whatever, containing the radicals, will meet each other to terminate to become a final polymer, okay, such as this. In this case, we have two radicals of the growing chain with the high molecular weight meet each other. So that's what we call the combination, combined together. So we call this as a combination or coupling reactions. Okay? Couple is you have two growing chains meet each other. So first case of the termination is coupling reaction or combination reactions. You can also describe this, termination reaction by coupling or combination, KTC. KT is a termination reaction rate constant, but C, another C, is coupling. So RT, excuse me, I think we can come back. And also we have disproportionation reaction, in other words, you have two different radicals, okay, growing chains, but you have two different, the physical chains without containing radicals. The difference between the first coupling and combination is that two growing chains will meet each other to form one big chain, one physical chains. Whereas in the second case, we have a two growing chain meet together, and you have a two polymers, two terminated spaces. That's the difference between coupling and the disproportionation reactions. So in terms of the molecular weight, if you have a termination reaction by the coupling, your molecular weight is doubled, whereas in the case of disproportionation reactions, your molecular weight is the same as your growing chain. So let's say that we can describe this radical containing big chain is called the kinetic chain. Okay, kinetic chain because it will be changing anyway because it's very active. Whereas you have a chain without containing radical, it's dead, okay, and it's terminated already. So we call this as a physical chain. Physical chain does not have any active spaces, and it's no longer active, reactive. So we call this as a physical chain. This is the kinetic chain. So let's summarize this reaction of the termination. So coupling reaction or combination reaction is the one that you have a two kinetic chain becomes one physical chains. Okay. Now disproportionation reaction can be described as a two kinetic chain will become two physical chains. Okay. Now the total termination reaction is governed by these two modes, so that we can describe the KT as KTC plus KTD because this is the randomly occurred. Okay. Remember that KT is in the order of 10 to 6 to 10 to 8, which is quite larger, much larger than the propagation reaction rate constant, and even much larger than the initiation reaction rate constant. So what happened? KT is very large. Okay, it's several orders of magnitude higher than even the propagation reaction rate constant. Anyway, the RT can be described that KT times you have two growing chains, two kinetic chains, m dot and m dot. So you can describe this RT as KT times m dot to the square, right? Okay. So if you know the monomer radical concentration of a growing chain, we can describe this RT. Now I have one question to you. I have emphasized the magnitude of KT. Okay, 10 to the minus 6 to 10 to the minus 10 to the 8. Physical, the propagation reaction rate constant is about 10 to the 2 to 10 to the 4. So KT is much larger than KP. No, I told you that KP is even larger than KI, and KT is even larger than KP. So what happened? My question is, even with this situation, KT is very larger, much larger than KP. Can you expect still the polymer from this reaction? No, you will not be able to make the polymer if the KT is this much larger, assuming that your KT and KP and Ki is linearly the proportional to your the reaction rate, okay? Affecting your reaction rate linearly. Okay? But that's not true. The assumption is not true. Okay? So I will show you overall reaction rate constant over reaction rate in terms of Ki, Kp, and Kt. Okay, so you have some suspect about the polymerization reactions. Keep in mind about that, and I think we can clear that out later on. Now, you all showed that Ri, Rp, and Rt, and it contains the known concentration of the monomer or unknown radical concentrations. Radical concentration can be detected by the electron spin resonance spectroscopy, detecting the concentration of your radicals, but it's not easy. Okay? Think about the reaction vessels. You put the monomers and initiators, and after some time, just like a condensation polymerization reactions, you take out some pieces of your reaction medium containing, radicals, containing monomers, and if you put it into ESL, you will be able to make the concentration measurements of the radicals. However, you have to do that from time to time, and you have to put that in the liquid nitrogen, because the radical concentration is not constant. It's changing because the radical is very active, very reactive. Okay, once you take it out, you have to, at room temperature, it's changing. It's gone. So what you have to do is that you have to put that, the reaction, the reactants mixture, put it into liquid nitrogen to cool down, so that you will, lower your reactivity of the radicals. But that's not easy. So what you should do later on is that we can have an assumption called a steady state assumption. So there is a way of removing the unknown radical concentration with the known variables, such as monomer concentration or initiator concentration. Okay, with that. So we will come back with the radical polymerization reactions. Now, fourth mode of termination is a chain transfer reaction. Okay? Well, we have our active species called the M n dot. So n could be some number, okay? And we have our S, which might be solvent, which might be the initiator, which might be a polymer itself or physical chain. And we'll give the radical to this active species. So you have a terminated physical chain with Mn with S dot. If you have a S dot could be, if S dot is reactive enough to become an initiator, yes, it will be reacting, but in many cases, S dot is not very active. Okay? It's not as reactive as Mn dot or initiator concentrations. So Mn dot is an active chain. Again, this is the kinetic chain, kinetic chain. S could be a monomer, could be solvent, could be polymer, could be a chain transfer reagent that we add this chain transfer reagent, purposely, right? Intentionally. We put this chain transfer agent to terminate the reactions. Okay, so Mn is a physical chain because it's that, again. So again, we can come back to the kinetic chain length, and kinetic chain length can be defined as as a radical chain polymerization, and the kinetic chain length mu is defined as the average number of monomer molecules consumed or polymerized per each radical, okay, for each radical which initiates a polymer chain. So if you have a growing chain, okay, and at the end of the chain you have a radical, that's a kinetic chain, and you can see how many repeating units that you have. Could be determined by the length. So if you have that type of a reaction, we can calculate the kinetic chain length. If you don't have any radicals, it's a physical chain, and you can determine those repeating units of the or degree of polymerization reaction as usual. Okay, as usual, what we have already done. For example, if you have a monomer molecule, we have a 4,000 monomer molecule, okay, and have about the 4 radicals. Let's assume that we have 4 radicals with the 4,000 monomers. Kinetic chain length will be about 1,000. Okay. Let's say that we can have this growing chain could be combined together to become the terminated by disproportionation. Then kinetic chain length is the same as physical chain length, but if the termination is done by disproportionation reactions. If you have a 4 kinetic chain terminated by coupling, okay, then molecular weight is doubled, so that the molecular weight of final molecular weight of this type of polymer will be 2,000 times your monomer, the molecular weight, right? And this could be determined by the different types of reactions. So physical chain can be determined by the all full reactions, whereas the kinetic chain length can be determined by the how many radicals that you have in your growing chains. Now we can describe this reaction and compare with the non-polymerized reactions. With the non-polymerized reactions. So far we talked about the polymerization reaction done by the radical polymerization reactions, but let's compare that type of polymerization reaction with non-polymerization reactions. If you don't have any the monomer containing double bonds, okay, then that's regarded as non-polymerized reactions. Let's say that we have an initiator, okay, the peroxide. It becomes 2 radicals. One of the radical will react the bromine. You form the RO bromine and the bromine radical, and the other one will attack the toluene, will terminate with the alcohol, with the benzyl radicals. In this case, we have one initiator, okay? One initiator will cleaved into 2 radicals, and one of these 2 radicals will attack this non-polymerization system. One is the bromine, the other one is the toluene. Okay? And the difference between the polymerization reaction and the non-polymerization reaction is that you have 2 radicals and form the 2 kinetic chains by the decomposition of this initiator. Okay? Anyway, there is no reactive sites in this case, so that's the difference between the initiation reaction from the non-polymerization reaction and polymerization reactions. If you look back at the polymerization reactions, we only have the one radical will attack the monomer, okay, and you have active sites, 1 radicals, without containing this. So that's the difference. If you look at the propagation reactions, one of this bromine and the benzyl radical will attack this each species to form the. I think you should have a radical here. You should have a radical here. But anyway, this is the same. So one kinetic chain attack the physical chain in the reactants will form the 1 physical chain and 1 kinetic chain. So number of active species are fixed, and some reactions are repeated during the kinetic chain reactions. That's the the typical characteristics of non-polymerization reactions. Termination reactions, if two kinetic chain meets each other, wherever the spaces you have a terminated spaces. Okay, I think you should remove this. Yes. You should remove this. So net reaction is that the one initiator can form the the several spaces, which is a little different from from the polymerization reactions. So you do not form the polymer here from the initiator, but you form the radical reactions, not radical polymerization reactions. Okay? You do not form the polymer, but you have a different species of the small molecular component from the non-polymerized radical reactions. Okay? So anyway, the non-polymerization reactions of the radical reaction is possible, but the mode and the type of the product is quite different from the radical polymerization reaction versus the non-polymerized, the radical reactions. Now, in fact, if you go back to the chain polymerization, chain gross polymerization reaction and radical polymerization reactions, we have as a function of time, if you look at the reaction rate, it follows this line, asymptotic line. So at the beginning, you have initiation reactions, and propagation reaction will be proceeded much faster, and it reaches the steady state, and it will follow the termination reaction, and you do not have any further reaction because the termination reaction is much faster, so that you will form the physical chain along the time scale around here. Okay? Now, the initiation reaction, as the initiation reaction follows, reaction rate is not great, and you form some sort of a lag time. In other words, reaction proceeded, but you do not have any the faster reaction rate. Lag time. Okay, lag time, so that the reaction rate is not great at the beginning. Okay? You need some time to proceed further onto the initiation reaction, and it reaches once it reaches the propagation, then your molecular weight will be slowly increasing. It reaches the steady state, and the termination will prevail the overall reaction, and you have a termination reactions. And at this stage, at the steady state, the initiation reaction rate and the termination reaction rate is equal. Okay? We assume that Ri is equal to Rt. If you remember Ri and Rt, and if you put it together, then you will be able to get the I dot and M dot, so that the I dot and M dot could be replaced with the known variables or constants. Anyway, this is the typical example of the chain gross polymerization reaction rate. So if we compare the chain polymerization reaction and the chain reaction, in the case of chain reaction, we have an induction period. Induction period is the one in this case here. Okay? Induction period, so that we need to have because of the presence of the inhibitor. Okay? Inhibitor, we have two different the specific components called the inhibitor and the scavenger. Okay? inhibitor or radical inhibitor and radical scavengers are two different types of reactants. Inhibitor means it delays, it slows down, it prohibits the formation of the radicals, whereas a scavenger is the one that it eats, it kills the radicals. Okay, scavenging is it destroyed the radicals. Inhibitor is the one that it prohibits the formation of the radicals. So this is the two opposite components. You put the inhibitor in your monomer. Okay, you put the inhibitor in your monomer, which contains the double bonds. For example, styrene monomer. Styrene monomer could form the radicals upon heating or upon exposure to the UV light. So during the storage of during the ship or transportation of this styrene monomer, this monomer could be exposed to the UV to the sunlight. So when you have a sunlight exposure for some time, styrene monomer will form radicals, and radicals will react to each other to form growing chain and polymers during the transportation, right? So in a long time ago, maybe about 100 years ago, the chemist in Europe found that if you have a styrene monomer is in liquid form at room temperature, but after some time, it becomes a solid. And they did not realize this is a polystyrene. They did realize at that time that there are some reactions, perhaps done by Lennard-Jones potential. I mean the dipole interaction or van der Waals interaction may form some type of different chemical than styrene monomer, and they did not realize this is a polymer. Okay, so anyway, during this transportation of your monomer, okay, we have to prohibit the monomer reactions to become polymer, which was unintentioned. Okay? So we need to put inhibitor or protector to form the radicals. Okay? That's why I think in order to have the inhibitor to be removed, we need a slow reaction at the beginning. This is what we call the induction period. So because of the presence of the inhibitor at the in the double bond containing monomer, we have some induction periods. So when the active centers are formed, reaction rate will be much faster and reaches a steady state. The overall reaction is reaching plateau region. As you see, this plateau region decreases due to the loss of the monomers or initiators. So at the plateau region, we can assume that at the steady state, Ri is equal to Rt, okay? which conflicts each other and terminates all. And this is the summary of what we have done already. So I think we can talk about later on about the difference between the free radical reaction and the ionic reaction as well. So far, we have talked about the chain-cross polymerization and the three very important aspects, and also the fourth important aspect called the chain transfer reaction. And particularly the termination reaction is governed by two important modes: coupling or combination and disproportionation reactions. So we don't know yet how many percentage of the combination, how many percentage of disproportionation, but we can sure that some portions are governed by some portion of the termination is governed by coupling, and the rest of them are governed by disproportionation. So we have to consider two modes. So we will come back to write the overall reaction rate of whole initiation to the chain transfer in one reaction equations. Okay, R. Okay, not Ri or Rp. Okay, so we will derive the R overall reaction rate and how this overall reaction rate will influence your degree of polymerization reactions. So we need to know what about the molecular weight, okay? How this Ki, Kp, and Kt will affect your degree of polymerization reaction rate. And what about the temperature? What about the temperature? If it increases the temperature, does increase of this temperature affect the R or dP, and so on? What about the concentration? If you increase the concentration of monomer, what happened? What about the concentration of initiator? Does it affect the overall reaction rate or dP? So those are the aspects that we will talk about next time after this. So far I think we can, you can easily follow because this has already been touched in organic chemistry course. Right? Remember that the problem set or homework set of about the step-cross polymerization reactions. You will need to submit a solution set so that we can grade and give it back to you, which might be helpful for your second exam. If not, then I would like to see you on Friday. Thank you.